Neel Somani has built a career that sits at the intersection of theory and practice. His work spans formal methods, machine learning safety, quantitative research, and large-scale systems. While many researchers focus on improving model performance or scaling infrastructure, Somani concentrates on a different question. How can we be confident that advanced machine learning systems behave in ways we actually understand and can rely on? Through academic research, industry experience, and entrepreneurial work, he has developed a perspective shaped by first principles. His background in computer science, mathematics, and business gives him a broad lens on problems that are often treated narrowly. In this interview-style feature, Somani explains how formal methods inform his approach to machine learning safety, why current safety practices fall short, and what realistic progress could look like in the years ahead. Somani's interest in formal methods began with a fascination for the limits of computation itself. As he describes it, formal methods appeal because they are grounded in logic and mathematical reasoning rather than heuristics or best guesses. Concepts like the halting problem are not just academic curiosities. They reveal hard boundaries on what algorithms can and cannot do, and those boundaries matter when systems are trusted with real-world decisions. During his undergraduate years at University of California, Berkeley, Somani worked in research environments that emphasized rigorous thinking. One formative experience was his time in Professor Don Song's lab, which focuses on security and privacy. There, he worked on proving that a machine learning algorithm satisfied the formal definition of differential privacy. That project marked his first serious exposure to applying formal reasoning to machine learning systems. What stood out to him was the contrast between informal claims and formal guarantees. In many areas of machine learning, researchers rely on experiments and intuition. Formal methods demand proof. That difference would later shape how he evaluates safety claims across the field. After graduating, Somani took his skills into a very different environment. He joined the commodities group at Citadel as a quantitative researcher. There, he encountered optimization problems that were not just theoretically complex but operationally critical. In the United States power market, for example, pricing and allocation are solved using large-scale mixed-integer optimization problems that are computationally hard. Working in this setting reinforced the idea that abstract theory has concrete consequences. Errors in reasoning or implementation can translate directly into financial loss or systemic instability. For Somani, this period underscored the value of correctness and robustness, not as academic ideals but as practical necessities. At the same time, it clarified the limits of what can be proven at scale. Many systems operate under assumptions that are never fully verified. This tension between what is desirable and what is feasible continues to define his research agenda. Somani's return to machine learning research was driven by a growing awareness that formal methods were underrepresented in the field. While machine learning had advanced rapidly, safety and interpretability lagged behind. There were few agreed-upon standards for certifying that a system was safe or even well understood. His early projects explored applying formal verification to GPU kernels, the low-level code that underpins many machine learning workloads. This work eventually led to CUC, a project that applies formal verification to GPU kernels written in Rust. The motivation was straightforward. GPUs lack many of the safeguards present in higher-level programming environments. Small bugs can introduce subtle errors that are difficult to detect and diagnose. By proving properties about these kernels, Somani aimed to eliminate entire classes of failure before they could affect model behavior. This approach reflects a broader theme in his work. Rather than attempting to verify entire models end-to-end, he focuses on specific components where formal guarantees are achievable today. According to Somani, current discussions around machine learning safety are still at an early stage. There is no widely accepted framework for certifying safety or interpretability. Many claims are based on limited testing or informal reasoning. Formal methods offer a different standard. They are the only tools that can establish principled guarantees about program behavior. For properties like robustness, where small changes in input should not produce extreme changes in output, testing alone is insufficient. Inputs exist on a continuum, and no finite test suite can cover all possibilities. Formal verification provides a way to reason about infinite input spaces. It allows researchers to prove that a model satisfies certain properties across all relevant cases. While applying these methods to full-scale models remains out of reach, Somani argues that dismissing them entirely is a mistake. One area where formal methods are particularly well suited is robustness. In practical terms, robustness means that a system behaves predictably under small perturbations. Without it, outputs become unreliable and trust erodes quickly. Another challenge lies in the correctness of low-level infrastructure. As machine learning systems grow more complex, they rely on increasingly specialized hardware and software stacks. Errors at this level can propagate upward, undermining higher-level guarantees. Somani's work demonstrates that formal verification can address these issues in targeted ways. By focusing on well-defined components, researchers can make meaningful progress without waiting for breakthroughs that would enable full system verification. One of Somani's more recent projects, symbolic circuit distillation, tackles a different problem. Interpretability research often relies on metaphors and informal explanations. Researchers identify circuits within models and propose stories about what those circuits represent. The difficulty is that these stories are hard to verify. There is rarely a way to prove whether an interpretation is accurate or merely suggestive. Symbolic circuit distillation attempts to close this gap. It extracts the program encoded by a circuit and then proves or disproves equivalence over a defined input space. This approach brings formal rigor to interpretability. Instead of relying on intuition, researchers can test whether their explanations precisely match model behavior. For Somani, this is a step toward making interpretability claims falsifiable rather than speculative. Somani is clear-eyed about where his work fits into the broader ecosystem. Most businesses do not inspect the internals of machine learning models. They use models as tools within workflows, often treating them as black boxes. His research is most relevant at the level of foundational models and infrastructure. Formal definitions of privacy or safety may be easy to state but difficult to verify in real systems. By implementing these methods on smaller examples, Somani aims to show that they are viable in principle. Some projects lean more heavily toward application than theory. KV Marketplace, for example, demonstrates how modifying an inference engine like VLLM can reduce recomputation by optimizing GPU caching. While not a formal methods project in the strict sense, it reflects the same concern for efficiency and correctness at scale. Somani encounters two recurring objections. The first is the belief that it is too early to apply formal methods to machine learning. His response is that this view overlooks practical opportunities. Projects like CUC and symbolic circuit distillation show that there are meaningful applications today. The second objection points to the history of ambitious verification efforts that failed to deliver on their promises. Somani acknowledges this history but rejects the conclusion that such work should be abandoned. Progress in computer science often comes from long-term efforts that initially seem impractical. Formal methods provide a direction for safety and interpretability research. Even when full verification is not possible, the discipline they impose can improve how systems are designed and evaluated. As machine learning systems grow larger and more autonomous, Somani expects formal specification to play a greater role. When components become standardized, it becomes more reasonable to invest in verifying them. He draws a parallel to CompCert, a formally verified compiler that became feasible only once compiler designs stabilized. He also suggests that machine learning architectures themselves may evolve to accommodate verification. Some current mechanisms, such as attention, are difficult to represent within existing verification frameworks. Future designs may trade some flexibility for greater tractability. In high-stakes domains like healthcare and finance, Somani believes formal verification should eventually cover entire workflows. While this is unrealistic today, rising expectations for automated systems may push the field in that direction. Somani's contribution to discussions around responsible and safe artificial intelligence lies in offering a technically grounded vision. Regulators and industry leaders are searching for standards that balance capability with accountability. Formal methods could provide a foundation for such standards, offering guarantees without crippling system performance.